When corn spread globally in the early 16th century, Europeans viewed it as a highly adaptable miracle crop. It was one of history's most successful agricultural transfers, taking root across Europe, Africa, and Asia. But there was a critical error in how it traveled. The adopting nations only exported the physical seed. They completely ignored the indigenous Mesoamerican cultural knowledge required to process it safely. For thousands of years, those communities prepared corn through an exact science called nixtamalization. They soaked and treated the dried kernels in an alkaline solution, often made with lime, before they would grind it into dough. This chemical wash serves a strict biological purpose. The alkaline solution breaks down the complex chemical bonds that keep niacin trapped in an inaccessible form, making the vitamin available for the body to use. When the grain was exported without those preparation instructions, impoverished populations across the globe who relied on untreated corn as a daily staple began to suffer from severe malnutrition. They developed a niacin deficiency known as pellagra. The symptoms were brutal: digestive breakdown, massive skin lesions, mental decline, and eventually death. Medical doctors spent years incorrectly blaming bad air or local infections. Treating a biological technology as simple hardware without its cultural software leads to disaster. Pellagra proved early on that corn demanded a highly specific human partnership. By the 20th century, modern science attempted to establish total dominance over the plant to force maximum possible yields. Researchers achieved this through hybrid breeding. This specialized genetic engineering method exploded productivity and consolidated farming into a capital-intensive commercial enterprise. But there is a biological catch. The seeds from a hybrid crop lose their vigor in the second generation, which effectively destroyed the ancient, self-sustaining practice of seed saving. That biological limitation engineered a relentless new economic machine. To maintain those high yields, farmers were now forced to continuously purchase new seeds, heavy machinery, and synthetic fertilizers every single year. In the pursuit of maximum output, corn production evolved into a high-input industrial loop that tied the farmer's survival directly to commercial manufacturing and global supply chains. This industrial success created a massive unintended consequence: drastic overabundance. The problem shifted from how to grow enough corn to where to put all of it. The surplus aggressively expanded into the foundations of the livestock feed industry. It flooded highly processed human food chains, appearing invisibly as refined syrups and starches. The sheer volume forced corn to breach the boundaries of the food system entirely. It became a foundational ingredient in industrial additives, plastics, and the fuel systems powering modern combustion engines. Sustaining this multifaceted demand requires an extreme agricultural footprint. Farmers now plant monocultures, massive land tracts devoted entirely to millions of genetically similar corn plants. Those unbroken fields carry severe ecological vulnerabilities. Genetically identical crops are highly susceptible to fast-spreading diseases. They plummet local biodiversity, and the endless fertilizer application creates toxic runoff. Every attempt to infinitely scale corn's productivity generated an equally massive systemic vulnerability, irrevocably tangling human environmental stability with the crop's demands. If you return your focus to the physical biology of the modern corn plant, you will find a strange weakness hidden inside its evolutionary success. The plant is completely trapped by its own architecture. The husks are too tight, and the seeds cannot scatter. If an ear falls to the ground, it simply rots. Corn cannot reproduce without human hands. Contrast that extreme biological frailty with the reality of modern human infrastructure, which now relies entirely on corn to prop up our global food, chemical, and energy supply chains. Because corn is the primary calorie source for global livestock and a critical industrial fuel component, a systemic failure of the crop would cause a cascading breakdown of our global food and energy distribution. We operate under the historical assumption of human mastery, believing we engineered a plant to feed the world. But looking at the invisible, inescapable architecture of our survival, the plant ultimately engineered us. Modern corn grows in tall, orderly rows that stretch to the horizon. It covers millions of acres worldwide, dominating massive swaths of arable land. It feeds human populations, sustains livestock, and powers industrial manufacturing. Harvesters pull millions of tons of cascading grain from the earth every single season, securing its position as an apex crop. But if the humans driving those harvesters were to suddenly vanish, this dominant organism would face an immediate biological crisis. The anatomy of the modern ear creates a trap. The thick husks are extremely difficult to penetrate, and the kernels are firmly anchored in tight rows to the central cob. If an ear falls to the ground unharvested, the plant goes nowhere. The seeds remain locked inside their casing. They rot on the stalk or decay in the soil without ever scattering across the earth. Natural selection dictates that a species must be able to reproduce on its own to survive. A plant completely incapable of planting itself contradicts the basic rules of biology. We have an organism that covers the globe but lacks the mechanical ability to drop a viable seed. This makes modern corn a highly flawed biological entity. Its existence relies entirely on human intervention to break open the ear and separate the kernels. 9,000 years ago, the hills of southern Mexico presented a very different landscape. Plants surviving in this environment received no irrigation, no protective cultivation, and no human care. They had to endure harsh conditions entirely on their own. One of the wild grasses growing in these hills was Teosinte. It was thin and scattered, producing a small handful of rock-hard seeds. It lacked the abundance of modern crops, but it functioned perfectly within its ecosystem. Teosinte produced a fragile seed casing that shattered upon maturity. This allowed the tiny kernels to drop to the soil and scatter in the wind without assistance. The kernels did not wait for a harvester. They actively separated themselves from the stalk to ensure their own survival. Teosinte offered very few calories to ancient foragers, but it possessed absolute evolutionary independence. Humans living in those hills began trying to extract more calories from this stubborn, low-yield grass. Generation after generation, farmers identified the rare Teosinte plants that produced slightly larger kernels. They isolated and replanted them. This timeline tracks 9,000 years of cultivation. It shows how the microscopic decisions of ancient farmers, repeated over millennia, slowly compound physical traits over time. The result of this intense selective pressure was a diverse array of varieties featuring massive, tightly packed cobs entirely divorced from the original wild grass. The visual gap between scattered seeds of Teosinte and the dense ears of corn is severe. For decades, modern geneticists struggled to accept that a plant as unimpressive as Teosinte could realistically be the direct ancestor of modern maize. The morphological leap appeared too vast for natural plant evolution. But eventually, modern DNA sequencing provided the absolute proof. The genetic record confirmed that ancient farmers engineered this massive transition through continuous selective breeding. By selecting for specific mutations over 9 millennia, these farmers created a physical divergence that would typically require millions of years of natural separation. The physical traits of modern corn, the impenetrable husks and tightly clinging kernels, make sense when viewed as features of intentional design. These elements were specifically chosen by humans to protect the kernels from pests and to keep the grain firmly attached for easier harvesting. This chart plots agricultural yield against biological independence. As human selection forces the yield to climb exponentially, the plant's natural autonomy drops in direct proportion. The selective breeding crossed a threshold. At this point, its ability to survive in the wild hit absolute zero. Modern corn functions as a piece of biological infrastructure, its internal structures optimized for storage and transport rather than independent reproduction. It boasts an incredibly high population count, yet exists in a permanent captive state. Its massive seeds are trapped by the very design that makes them useful. By isolating traits that feed entire civilizations, humanity stripped the plant of its reproductive freedom. We built an organism inextricably tied to our own survival, ensuring that as long as corn exists, it requires human hands to plant it.